Hi, today I'm going to talk about moving between circular orbits in a gravitational system, a simple two-body gravitational system with one large mass and one very small mass, a satellite going around the Earth. I'm making this video for my undergraduate class. We call it Physics 130 at my university. It's the first semester physics course that science majors generally take. I'm just doing this to fill in a few details because when I went over it in class this semester, spring 22, I skipped some details that I want to fill in now. That said, if somebody's taking an intermediate mechanics course, which we call Physics 310 on our campus, this might be good review before you start that course because this is the freshman level. To get through this video, you should be past the point in your course where we do what I call a backward derivation of Kepler's laws. That is, historically, Newton formulated his theory of gravity by using Kepler's laws, and typically in these freshman classes, we give you Newton's law of universal gravitation, and from it we derive Kepler's laws. You should be familiar with that derivation and comfortable with that level of work. Uh, really, there's no calculus in what I'm about to do. You only need to be able to do high school algebra to get through this. So you could probably get through this in a lower level course, maybe even high school physics if you're really good at it. The physical problem here, I need to state more explicitly. I start with a satellite in a circular orbit around the Earth, and I say small, meaning I'm treating this as though the Earth is infinitely massive compared to the satellite. So there's my silly little picture. I've got the Earth and I've got a circular orbit. It can be a low Earth orbit or mid-range orbit. I don't care. It just has to be circular. If I want to move to a higher orbit, one that's farther away from the Earth, the basic question is how do I get there efficiently? So the presumption is that we have thruster engines, some kind of engine that can add a large amount of kinetic energy in a short burst. Short burst, by that I mean that the time during which I change the energy is negligible. So suddenly I go from whatever energy I had to a higher amount of kinetic energy, short in time and therefore acting at one point in the orbit. So I can suddenly add, which is not really so unrealistic. The time to go around even a low Earth orbit is about an hour and a half. Once I get to higher orbits, it can be arbitrarily long. The amount of time for the engines to run would be minutes. So get down to the physics. We know that the total energy in an elliptical orbit inversely proportional to the length of the semi-major axis, right? That is the formula. Remember, it's a negative total energy, which is equal to the negative of the kinetic energy, and it's 1/2 of the gravitational potential energy. Again, a semi-major axis. The two masses, the mass of the Earth, the mass of the satellite, and big G, Newton's gravitational constant. I note that the formula also works for circles. Circles don't have a semi-major axis, but the semi-major and semi-minor axis are degenerate, and they're both just the radius of the circle. So in that formula, you would replace the A with an R for the radius of the orbit. And if I want to calculate, I'm going to assume that we're always looking at elliptical orbits because that's what I get in a gravitational system. I'm going to go in some elliptical orbit that goes from my initial orbit and makes it just out to my final orbit. You might think, well, why don't I just add all the energy right away? If I added all the energy I need right away at some point, I would end up overshooting and getting an elliptical orbit that just goes through the same point but goes past the orbit I want. To do the math, I'm going to make this little substitution. I use the Greek letter mu for no particular reason, just to put all the constants that aren't going to change together. I've got Newton's gravitational constant, the two masses, over 2. And then the energy of an orbit is just mu over the semi-major axis. The minus sign is incorporated into the mu. So there's my generic form for the energy of an orbit. And I've proposed an elliptical orbit that goes tangent to both circles. It just gets from the initial circular orbit, just makes it out to the distance of the larger orbit. Now, I need to know the semi-major axis of that, the length of the semi-major axis. I have, for the semi-major axis, I've got the radius of the small orbit plus the radius of the large orbit. That gives me the full major axis, the longest length within the ellipse. The semi-major axis is half of that, which is the average of the two circular orbit radii. So I call it the transit orbit. There's probably a better technical name that satellite people use. I'm not a satellite person. This orbit, the dashed reddish curve, has that for semi-major axis. So I can calculate its energy really easily. I can calculate all the energies I need. I've got the inner orbit, the final orbit, and the so-called transit orbit. The differences of these will tell me the energies I need to add. So before I get to the simple answer in this notation, I want to look first at how much total energy I'm going to need to go from the initial to the final orbit. I can compare that later to check and see that it really was an efficient process that I chose. Well, the required energy is just, the energy is mu over r, so it's mu over the larger radius minus the smaller radius. Remember, there is a minus sign incorporated into mu. Therefore, I'm going to have a positive total energy required. Sorry about that. If I clean up the algebra a little bit, most people would prefer to write this way. I get the difference in radii over the product of the radii. Now I go back and say what I really wanted to know was how much at each stage to fire my thruster engines. So I want to find the energy to add in going from the initial orbit to this so-called transit orbit. And then I'm going to do separately the energy to go from the transit orbit to the final orbit. Remember that transit orbit being more highly elliptical has a maximum potential energy out where it's farthest from the Earth. So it's a minimum kinetic energy. So it's not going very fast there, which is why I need to add energy to get up to the speed necessary for the outer circular orbit. So this is just arithmetic at this point. The first energy burst I need to release to get from the initial to the transit orbit is just mu times difference in 1 over radii, or 1 over semi-major axis. And again, the semi-major axis for the transit orbit was the average of the radii of the circular orbit, so I've got that 2 in the numerator. The form looks pretty similar for the other burst I need to add. And the form looks pretty similar there. Really, in a sense, as I posed the problem asking how much energy to add, I'm done. Those are the answers. I might want to clean them up a bit so they look more similar. It's just a little bit of algebra. And then I'm going to compare the total here to the total I calculated to switch orbits from one to the other, the difference in energies, just to make sure that I'm being honest with myself, check my algebra, make sure I chose an efficient transit orbit. So my cleaning up, I just get a common denominator, I factor things out, and I've got the same first factor there. After mu, I've got R1 minus R2 over the sum, so the difference over the sum. But in the first case, the amount of energy I add is proportional to 1 over the first orbit, and in the second case, 1 over the second orbit. Second orbit is larger, that means I'm adding less energy. the second time, which you may have guessed with some physical kind of intuition and figuring, but you don't need to. That's what the algebra gives us. So again, as the question was posed, these are the answers. You just have to remember that that mu is negative g times the product of masses over 2, right? And the minus sign with the mu is canceled by the fact that R1 minus R2 is a negative number as well. So these are both positive energies, which is what you expect. You need to add energy to get to a bigger orbit, of course. So I keep mentioning that I should check it. What I need to do is compare the, the total of these two to the total minimum needed. Frankly, you should do the algebra yourself. It's not that hard. It does indeed work. If I add up these two delta E's, I find that that is the same as what I got for the total required. So it was an efficient process. I did not waste energy by doing that. I know this wasn't a very big example, but I wanted to make sure all those details were filled in. That is the right way to get a satellite from one orbit to another. That's all there is to it. See you in class.